Okay, so probably the final lecture of the course. Here in this lecture, we will see at the time varying fields, right? We saw electrostatic, we saw magnetostatic. We gradually built the case for the time varying field in our last class when we multiplied the capacitance per unit length of the coaxial cable with the inductance per unit length of the coaxial cable, and we end up on the square of the phase, inverse square of the phase velocity of the electromagnetic wave in the coaxial cable, right? So we saw many things previously in the electrostatics and magnetostatics. Now we will bring few minor changes in those concepts to build new cases for the time varying fields. In the time varying, you remember previously we saw that E dot dl. Um,
सर स्क्रीन शेयर नहीं की हुई.
E dot dl was E dot dl was equal to uh, E dot dl was equal to from A to B was equal to VAB, right? And when it was a closed loop integral, E dot dl for a closed loop integral, or you say if you come back to the same point, you end up on zero value. That was the we call this law as the KVL, if you remember. Now again we have the same law in the time varying fields, and but this time we say that the E dot dl equation, which was the KVL thing, but this can be produced. For example, if say this is the wire, right? If this say this is some kind of wire, and let we take some differential length of the wire, and then if we say if there's a magnetic field B passing through it, right? And say that a magnetic field B is not constant, is not the magnetostatic, it's the time varying magnetic field. Okay, so say the partial derivative or the derivative of this magnetic field, or the full derivative of this magnetic field with respect to time is not zero, meaning that B is not magnetostatic. B, if this is not equals to zero, this means the B field isn't magnetostatic. Okay, so that means B is very varying in time. So when that's true, then when this is true, when the partial derivative of the magnetic field with time is not zero, the full derivative is not zero, then B dot ds and it's the surface integral of this with respect to time is going to give us the electric voltage in a closed loop. Okay, electric voltage in a closed loop, remember, closed path. And we call this as the we call this thing as the EMF. Okay, we call this as call this one as EMF. Okay, so see, there's a little difference here. In previously we said that when the electric field in electrostatics, when the when the charges are statics, in the electrostatics, when the charges are static, the closed loop integral E dot dl was going to be zero. But now, when the magnetic field is changing in time, this is producing an EMF. So when say this is a conductor, okay, and say the closed path, and B is time varying. By time varying, we mean it's the time derivative is not zero. Then then they produce a voltage in this path. There's a voltage, there's EMF in this path. Even if you open this path, say from the 2 points, say if it's not fully closed, you'll get that voltage in both cases. In the electrostatic, you'll get that voltage. In the time varying fields, you'll get that voltage. But in time varying fields, even if this path is closed, you are going to get the EMF in the path. So that's really a kind of concept introduced first by the Faraday. And he said when the Faraday was basically uh, uh, the Faraday at his time, he was conducting numerous experiments on the uh, on the electromagnetism, right? It was Ørsted. It was Ørsted back in 1819. He said when there's a conductor, and that's carrying current high, you will end up on a magnetic field around it. That's was the Ørsted discovery, and that was the profound discovery in the electricity, in the field of electromagnetism, in the field of electricity. Ørsted demonstrated that if a if a wire carrying current, um, if a wire is carrying a current I, then the magnetic field will encircle it, and it establishes the relationship between electricity and magnetism. Then later on, then later on, that was the Ørsted experiment. So if current I is moving through the wire, you get the magnetic field around it. The Faraday very soon after the Ørsted discovery was in opinion that the reverse of this experiment must also be true. Meaning, if there is a magnetic field, if there's a magnetic field, that should produce produce current high. And for that purpose, Faraday developed an experiment. And he by that time, remember, only the DC volt was known, and there was a battery, right? So the static things were known. So what the Faraday did, he introduced a switch here in the circuit, right? And he what he did, he he passed he made a big coil here. And you know that when we have this sort of coil, what happens, the magnetic field will be like this, will be through the solenoid. This magnetic lines of force will eventually come back to make a complete path. And there will be many such magnetic lines of forces, right? You know that. So what the Faraday did, he he took a primary coil, and then he placed a secondary coil here, and he placed an ammeter here, just to show the current I in the circuit. But for years, Faraday didn't discover that the magnetic field, this magnetic field, the black lines, when they pass through the green conductor, they produce current I in the circuit. He didn't observe that. And he concluded that the reverse of the Ørsted experiment is not true. It will not happen. Magnetic field, a steady magnetic field, will not produce current I. But one day when he was about to close down this switch, he momentarily saw some deflection here, and that deflection very soon perished. And then when he opened the switch, and then again he saw some a very brief deflection in this conductor, and he continued on an experiment, and he found that if we are closing down this switch, turning on and off, that means this magnetic field will be a time varying magnetic field. When you turn down, when you close the circuit, current I will start flowing through the circuit, and that current I in the circuit will have this sort of graph. If this is our time and say this is current I, the current I will not suddenly rise to maximum value. However, the current I in this circuit will take a little bit time to rise to the maximum value. This is I max. Okay, so in this duration, in this time delta, the current I is changing in time, changing in time. So hence, in this delta, this magnetic field is changing in time, in delta time. Okay. So Faraday concluded that a time varying magnetic field is going to produce a time varying current. So that was a profound discovery made at that time, and this gave us a very popular Faraday's law. Then then Faraday concluded that if this is say the loop number one, so in this loop some volt V will be induced, EMF will be induced here. Let I call this as the EMF. Some volt induced will be here, EMF. Then what Faraday did next, instead a single loop, instead a single loop like this, he placed another loop here, and he saw that another EMF2 is produced here. This was EMF1, this was EMF2 in the second loop. And then he placed a third loop. And then he saw that there's another EMF3 in the circuit is produced. So then he concluded that the induced EMF in the circuit is proportional to the area. So the induced EMF is proportional to the area of the loop. And this induced EMF is also proportional to number of turns. The more the turns you apply here, the more the magnetic field will cut down that, and you'll get the more EMF. So that was a very profound discovery in the history of electricity. So that was the Faraday's law. Then the E dot dl is going to give you the if a magnetic field is passing through it, and that magnetic field is changing in time. For example, this is a conductor, right? Just we said this is a conductor, and said this is a magnet. Said this is the north side, this is south. So if you move up and down this bar magnet, if you move it up and down, you move it here, the north and the south. If you move it up and down, you're going to change the magnetic field in time, and that will cause EMF here, and that will induce current here in this wire. Okay, that was the Faraday's experiment. So then see a very typical example of this time varying phenomena is in our cars, right? We need for ignition purpose, for the engine, we need 40,000 volts to create a spark, and that plug is going to cause, here is 40,000 volts you need to generate this to create a spark, and that will cause the ignition system to work. If the spark is there, then the fuel will start burning. Okay, so how to get these 40,000 volts? In the car, you have the DC 12 volts. What you do, you place a switch here, a transistor. So you turn on the transistor, it's a high volt. You turn off the transistor, it's a low volt. High volt and low volt, high volt and low volt, it's the time varying volt now. When you give it to the primary of this little transformer in the circuit, the transformer will enhance, will step up this volts to 40,000, and the car ignition system will start working. So this was one application of, you will find many applications of Faraday's law around you, many. Okay, so So where the Faraday's law, this was the Faraday. Remember, this is the dot, right? This little square is just a little problem with the uh, fonts of the PowerPoint. This was I'm not getting this dot here. By the way, this little square is not the square thing; it's the dot actually. So this was the Faraday's law. If you apply Stokes theorem on this Faraday's law and you do some manipulation, you are going to get this particular equation. And this is now the third Maxwell's equation. It simply tells you that if the magnetic field is changing in time, if this thing is not zero, this thing is not zero, if the magnetic field is changing in time, the electric field will change itself in space. That's very interesting. Look, the del operator is partial by partial x in the direction x plus partial by partial y in the direction y plus partial by partial z in the direction z. And del operator cross with another field is going to give you curls. Okay, it's going to give you curls. What was the curls? Curls was the closed loop, revolutions per unit area. So if magnetic field is changing in time, the electric field will be in the form of curls, right? And they will move. Those electric field, those electric curls will move because they will change. This electric field will change its position in space because del operator is a space parameter. Del operator is a space, or change in the space, change in the position of a point to another position. See, from this point you change things to here. So partial by partial x, partial by partial is change in the space. Okay. So if magnetic field is changing in time, you are going to get the changes in the electric field in the form of curls in space. That's the third Maxwell equation, or basically, this is an alternate form of the Faraday's law. It just tell you the Faraday's law is going to tell you that if magnetic field is changing in time, it's going to give you the voltage, EMF. So in the secondary coil, if magnetic field is changing in time, in the secondary coil you will get the EMF. Okay, the Maxwell translates this thing into a different way, and it tells you if magnetic field is changing in time, it's going to give you the electric field curls. Okay, so just go through this little derivation, very simple one, just apply the Stokes theorem and you'll get it. So that's the third Maxwell equation, a very profound discovery in the time varying field. This is for the time varying fields. Okay. If you do little bit mathematics, now suppose I take an example. I take an example. This is our Maxwell equation, and we say this B, say the B is constant, so its derivative is zero. When the derivative is zero, B is magnetostatic. And magnetostatic we mean if this is a wire, right, and the magnet is here and you are not moving the magnet is stable, you are not going to move the magnet. So if you are not moving the magnet, it will induce nothing in the wire, it will induce nothing in this, it will induce nothing in this wire, in this conductor. Okay, if the magnetic field is not moving, it will induce nothing. But if you start moving up and down, it will cause induction in this conductor, in this one. Okay, so that's the Faraday's law. So when this thing is zero, so then when the magnetic field is static, when the magnetic field is static, curl of E is zero. That means electric field is static, and static electric field has straight lines of forces, not curls, not loops, not the revolutions. Okay, so it's very much. Now, I have intentionally removed the derivation of this fourth Maxwell equation. I will upload. I will upload two lectures with the name of week 16 be detailed. In this, you will find the derivation of this thing in the fourth Maxwell equation. I'll upload a second file with the today's file by the name of week 16 be detailed. In that file, you will get the derivation of this thing. However, it's very much similar to a third Maxwell equation. It means if the electric field curl of H is equal to partial epsilon not epsilon R E divided by partial T. So I can really knock out these things, these constants outside plus another thing J. So if the electric field is time varying, it's going to give you the curl of the magnetic field. So it's that simple. In the static case, curl of H was equal to J. That was the Ampere's law in the static case. In the time varying case, you have partial D by partial T. That's an extra thing you're going to get for the time varying field. So this is fourth Maxwell equation, very similar to the third Maxwell equation. It's just the reverse of the third Maxwell equation, and it says if the electric field is time varying, it's going to give you the curl of magnetic field. The third equation says if the magnetic field is time varying, it's going to give you the curl of the electric field. So the two very much similar equations, like opposite to you. You can say the reverse of each other. So if you have if you have the electric field, you're going to get the magnetic field. Reverse is also true. If you have the magnetic field, you're going to get the electric field. Remember, if you have the electric field, you have the voltage. You remember that. Okay. And if you have the voltage, you have the current I. If you have current I, you get the magnetic field. Yeah? So very familiar things we have. Reverse is also true. You can go the other way around in this cycle. Okay, so time varying, if things are time varying, if one of the field is time varying, you get very interesting situation. Okay, so now we have the third and the fourth Maxwell equation. These two, this is the first Maxwell equation, the second Maxwell equation. These two are for static fields, for the electrostatics and for the magnetostatics. And this one is the time varying, third Maxwell equation, time varying, fourth Maxwell equation. When you solve these two equations simultaneously, when you solve third and fourth Maxwell's equations simultaneously, you will get the solution of electromagnetic wave, right? So when you solve the third and the fourth equation simultaneously, the solution is provided in week 16b detailed file. Just check for that. Okay, it's a derivation. For a while, I'll skip this. I'll skip this derivation. Okay. So when you solve the third and the fourth Maxwell equation, you will get an electromagnetic wave, solution of electromagnetic wave. So when you solve the third equation, the fourth equation simultaneously, you will get the electromagnetic wave. Sunlight is electromagnetic wave. Our Wi-Fi signal is electromagnetic wave. Our GSM signal is electromagnetic wave. Okay, so you are going to get the solution of the electromagnetic wave when you solve them together. Okay. Okay, we'll shortly see the solution. However, however, I'll not be deriving this solution in this class. I'll provide that to you in this lecture, in this file. Go through it if you need. However, for a while, we'll skip this derivation. Okay. So if I take, if you closely see, these are the four Maxwell equations, and all are in the differential form. All are in the differential form. You can transform them into integral form. Like if you take the third Maxwell equation and take the integral on both sides, this is the third Maxwell equation in the integral form. Similarly, you'll get the fourth Maxwell equation in the integral form. So that's a little thing you can you can do some mathematics to if you want to change the shape of the Maxwell equation from the differential form to the integral form. So sometimes maybe the integral form is more useful for you. So these are the four Maxwell equation in the integral form. And again, I'll not be spending much time in our last lecture on this thing. So, and your next class will basically, your next course will basically start right from here, right? That's the antenna and wave propagations. So these are the four Maxwell equations these are the four Maxwell equations in the integral form. Okay. Now, as I said, when you solve third and fourth Maxwell's equations simultaneously, this will lead you to the EM wave. It will give you electromagnetic wave. So let's see how that electromagnetic wave will look like. So let's see the EM wave. Okay. So I'm not going into a lot of details, but when you solve the third and fourth Maxwell equations simultaneously, you will get six possible situations. You'll get six possible solutions. Okay. At one time, for one electromagnetic wave, only one of the solution will exist. Okay. However, you are going to get six possible situations. But at one time, if you consider one of the equation, it will do your job. You will solve very complicated numericals if you consider only one of them for one instant. However, generally speaking, if you solve the third and fourth Maxwell equation simultaneously, you will get all these six possible situations. This, for example, this is vector Ex, H of X, H of Y, right? They are the electromagnetic, they are the fields of the EM wave in different direction. By EY, we means if electromagnetic wave, if this is the electromagnetic wave, say this is the Z direction, and say this one is, can make it like this is Y direction, and this one is suppose X direction. So if the electric field is oscillating in Y direction, let I make a simple case. If say the electric field is oscillating in X direction, and the wave is moving in Z direction, the electric field, this is Ex. because this is the x-axis. So it's oscillating along x-axis and it's moving in the z direction. Okay, so the electric field is oscillating in x direction and it's moving in the red z direction. Okay, so the electric field is Ex. Okay, so this equation is going to give you the electric field which is oscillating in the x direction. The magnetic field is oscillating, must oscillate in y direction. So along the y, the magnetic field shall oscillate. I hope I'm able to make this diagram clear. When the electric field is maximum, the magnetic field is also maximum. The electric field is maximum in the other direction, the magnetic field is maximum in the other direction. You can see. I hope this is clear. We'll shortly see a much clearer diagram of this. Right? So the magnetic field is oscillating in y direction, and here is the magnetic field which is oscillating in y direction. So this electromagnetic wave, this electromagnetic wave has equation 2 showing the electric field and equation 5 showing the magnetic field, this electromagnetic wave. Okay, and the wave is moving in the z direction. So this Ex, second derivative of Ex with respect to z minus j omega mu omega is the frequency of the wave, 2 pi f, this frequency. Okay, you know that. Mu is mu naught mu r, the medium parameter. Okay, and then sigma is conductivity of the medium. We discussed sigma in chapter 5. Okay, so here you see in the first 9 chapters we are revisiting many things from first 7-8 chapters. This conductivity, this j is imaginary, omega is again the angular frequency of the pi f thing. Epsilon is again equals to epsilon naught epsilon r, and it's the medium parameter. Okay, so this entire thing is called as gamma square. Gamma is propagation constant. Gamma is going to tell you the complete story of EM wave propagation. So gamma is going to tell you everything about the electromagnetic wave which has certain frequency and which is moving through certain medium. Medium is mu and epsilon. So a wave which is moving through certain medium, having certain mu, having certain epsilon, having certain conductivity of the medium, having certain frequency of the wave, what will happen to the wave after a second or 10 seconds or say 100 kilometers? What will happen to the electromagnetic wave? What will happen to the energy of the electromagnetic wave? An entire journey of the electromagnetic wave will be represented by the gamma term. It's called as propagation constant. This is equal to alpha plus j beta. Alpha is the phase constant. This is the attenuation constant. Alpha is attenuation constant and beta is phase constant. Okay, so this thing is going to give you the complete journey. If I look back closely to this equation, this is the maximum electric field, the green one. This is Ex naught. maximum electric field. And this one is the maximum magnetic field. It is H magnetic field, maximum magnetic field in the direction of Y. And since the maximum value, let I call this Y naught, Hy naught. Now, the relationship between Ex naught and Hy naught is J gamma omega mu. This is the relationship between Ex naught and Hy naught. So if I only know one equation, either 2 or equation 5, I can fully explain this electromagnetic wave. This electromagnetic wave. So if I know, if I'm able to understand, or if I'm able to model only one of the equations, either equation 2, or equation 5, right? If either I know the equation 2 or equation 5, one of them, and I know this equation star, this one, so I will be able to fully characterize the electromagnetic wave. Okay, if I know one equation 2, I can find the other one. I can find, if I know the 2, I can find the 5. If I know this equation also, if I know 5, I can find out the other one. Okay, so this Ex naught, if I write this Ex naught, this electric field will be equals to Ex naught, the maximum value. Suppose the sine wave, sine of this thing, and it will be omega t plus minus gamma z in the direction of x. Okay, gamma is the propagation constant. Okay, which is shown here. This is gamma. This is gamma square. Okay, this thing is gamma square, right? So gamma plus minus omega t, omega is the frequency. So I can really make this thing. If I know this equation, I can really calculate. The magnetic field. Magnetic field will be Hy naught. Sorry, Hy. This one, this magnetic field, it will be Hy equals to Hy naught sine of